Another way that we can estimate the enthalpy of a reaction is from bond energies. Because in a chemical reaction, we have to break bonds of our reactants and then form new bonds when we create our new products. And so we can estimate our enthalpy of reaction by comparing how much it takes to break a bond, how much energy goes into that, versus how much comes out when we form new bonds. The bond energy, that the definition of that is the amount of energy it takes to break a mole of a bond, which is kind of a weird thing to think about. And it kind of assumes that you're in the gas state and that the bond will completely be broken evenly. So one electron goes to one atom and one electron goes to another if it's a single bond. So we are going to be looking at tables of bond energies, and that will depend on, those values will depend on what those molecules are bonded to, as well as the other atoms that are around it. But we can generally get a pretty good estimate from the average bond energies. And so, like I already said, it works best when it's in the gas state. So because bond breaking, to break a bond, things that just doesn't happen spontaneously, that's endothermic. So the value is going to be positive. We're going to have to add energy in to break the bonds. Where when we form bonds, it's going to be exothermic. Energy gets released when bonds are formed. And so we're going to be comparing, keep in mind that our reactants are what we're breaking. So those are going to be positive values. And our products are going to be negative because they are the ones that are having bonds being formed. So our overall reaction is, for enthalpy of reaction, is the sum of all the bonds that we break, which will be a positive value, added to the sum of all the bonds that are formed, which will be a negative. So you have a positive plus a negative number. So in general, we talked about this last semester, but there are some trends in bond energies, and it just really has to do with, well, one, how many electrons are being shared. So if something that has 3 bonds, we have 6 electrons being shared, then it's going to take a lot more energy to break that apart. So we're going to be comparing like atoms. So for example, carbon and carbon in all of these cases versus carbon and nitrogen in these cases. We also will consider the length of the bond. So the closer they are together, or the shorter the bond, the stronger the bond as well. So if I have molecules or a bond where I have like a bromine and a fluorine versus bromine and chlorine and bromine and bromine, this is getting bigger as we go this way, and so they're getting further apart, so that bond is getting weaker. We can see that there. So we'll find these tables. So table 9.3 is what you'll use to look up the bonds that are the energy of every bond. So if we look at this example here, we have methane, CH4, plus chlorine going to form chloromethane and hydrogen chloride. So in order to break the bond, so to create our products, we have to break off one of those hydrogen-carbon bonds and break the chlorine-chlorine bond. So I'll look up how much energy it takes to break those apart and how much energy it takes to break those apart, all being endothermic. Now I'm going to be creating this new bond and creating this new bond. So I'll look up the energy that are associated with those and put a negative sign in front of it. And then I compare the two, so we can see that more energy got released when those bonds got formed, so the overall reaction would be exothermic. Now, in many cases, we're going to break all the bonds from our reactants and form completely new bonds for our products. So you'll want to make sure you draw your Lewis structures correctly, and then keep track of what bonds are being broken. But sometimes you don't actually have to break every bond, and so in those cases, it's kind of nice. So here I have methane and water reacting to form hydrogen and carbon. So I'm going to first start off by writing out my Lewis structures. So I have CH4, and then 2 waters. So I have 2 times water. It looks like this. And then I'm forming 4 HH bonds and then 1 carbon dioxide. So, whoops. So now you want to look at what bonds are you going to be breaking and which bonds are you going to be forming. So it looks like we don't have any original bonds, so we're going to be breaking all of our bonds of our reactants and forming all new bonds in our product. So what I like to do is go and count the types of bonds and keep track of them. So I have 1, 2, 3, 4 carbon-hydrogen bonds in my reactants. So I'm going to do all of my bonds broken first. I have 4 of those. I only have 1 methane, so I just have 4 of those bonds. Now I have 2 waters, and each water has 2 oxygen-hydrogen bonds. So I have 1, 2, with a total of 2, so 4 oxygen-hydrogen bonds. Now when I think about the bonds that I'm going to be forming, I have 4 hydrogen-hydrogen bonds, single bonds, and I have 1, 2 carbon, oxygen double bonds. So what we want to do now is actually just plug in values for that. So we'd go look at a table, and the carbon-hydrogen single bond is 414 joules, or kilojoules I mean, per mole. So I have 4 times 414. And then for oxygen-hydrogen, I have 4 of them, and the value in the book is 464 kilojoules. So the amount of energy that goes into breaking bonds is, 3512 kilojoules. So breaking. So that'll be a positive value. And then for my bonds being formed, I have 4 hydrogen-hydrogen bonds. Now those are each 436 kilojoules, and carbon-oxygen double bond, 2 of them, and it's 799 kilojoules. So if I look at the amount of energy that's going to get formed when I create new bonds, that is equal to 3342 kilojoules. So because I'm forming bonds, that's going to be release. I'm going to release energy, so that'll be negative. Basically what I do is I do broken minus formed. So here's how much it broken minus how much I formed. And so I'll take the difference, and the answer is 170 kilojoules. So a positive value. So this reaction is endothermic. Okay, here's another one. We're going to look at methanol, CH3OH. It's combusting in oxygen. And remember combustions, we go to CO2 and water. So we need to balance it. So over here I have carbon, hydrogen, oxygen. On my reactant side I have 1 carbon, I have 2 oxygens, and I have 4 hydrogens. Products, I have 1 carbon, 3 oxygens, and 2 hydrogens. So in order to balance it, I'm going to need to get 2 waters, making this 4 hydrogens, and then I have 4 oxygens. And then I'm going, but now I have oxygen that's split. So, and I'm realizing this should actually be a 3 there for my oxygen. So since I have 1 here and 1 here, so I'm actually just gonna look at how much is left. So I have 2 from oxygen and then 3 on the other side. So I'm actually gonna have 3 halves here, making that balance out. So you could multiply everybody by 2, but we're gonna do it for combustion of 1 mole of methanol. You can do it, multiply it out by 2, but then you're gonna need to ultimately divide by 2 to get it per mole of methanol at the end. So now I need to draw the molecules. So I'm going to have CH3, so methanol looks like this, OH, and then I have 3 halves oxygen, and oxygen is double bonded like that. Then I have CO2, one of them, and then I have 2 waters, so H2O. Okay, so here we go again. We're going to count up our bonds. So I have 1, 2, 3 carbon-hydrogen bonds. I have 1 carbon-oxygen single bond. And I have 1 oxygen-hydrogen bond. I also have 3 halves of an oxygen double bond, oxygen-oxygen double bond to break. Okay, for my products, I have 1, 2 carbon-oxygen bonds, double bonds, and I have 2 carbon-oxygen, or 2 water, in oxygen-hydrogen bonds in water, but I have 2 waters, so I'm gonna have 4 oxygen-hydrogen bonds. Notice I have 1 here and 4 on the other side, so technically I only have 3 total. So if you want to take that into account, you totally can. So I'm going to find the values. So 3 times carbon-hydrogen is, the carbon-hydrogen is 414. I have 1 oxygen-carbon, which is 360. I have 1 oxygen-hydrogen, that's 464. And I have 3 halves oxygen-oxygen double bond, which is 498. Okay, so that's how much I'm going to break. Now in my formation, I have 2 times carbon-oxygen double bond. That is 799. Oops. And then I have 4 oxygen-hydrogen single bonds, so 464. So the amount, so I'm going to do broken minus formed. The amount I broke is, the total is 2813 kilojoules. And I formed, so I'm going to do minus formed, 3454 kilojoules. So that number came from here, and this number came from there. So my total is negative 641 kilojoules. So that's how much energy was released, so exothermic reaction. Okay, last one we have the reaction of forming ammonia from its base element. So I have nitrogen. So I have nitrogen is triple bonded, nitrogen. And then I have 3 hydrogens. It's a single bond going to form 2 ammonia. So I have NH3. Okay, so the things I need to break, I have 1 nitrogen-nitrogen triple bond. I have 3 hydrogen single bonds. And I'm going to break 1, 2, 3 from ammonia, but I have 2 ammonia, so I have 6 nitrogen-hydrogen single bonds. Great, so plugging in numbers, nitrogen-nitrogen double bond is 946 kilojoules. And then I have 3 of hydrogen-hydrogen, which is 436 kilojoules. So the amount that I'm going to use to break is 2254 kilojoules. Great. And now for nitrogen-hydrogen single bond, I have 6 total bonds, and each of those is 389 kilojoules. So the total amount that I'm breaking is 2334 kilojoules. So broken minus formed. So I end up getting delta H equals negative 81 kilojoules. The next way that we're going to find the enthalpy or approximate it is from the standard conditions or standard enthalpy of formation. How this is defined is by a certain set of conditions. A standard state being 1 atmosphere of pressure. When we have a pure or solid liquid, it's always in its stable form at 1 atmosphere and at 25 degrees Celsius. And then if we are in a solution, it's going to be in exactly 1 molar concentration. How we denote that something's in the standard state is by putting a little circle up above. So that little circle right here shows us that we're dealing with enthalpy in the standard state. And when we talk about enthalpies of formation, we're talking about the enthalpy associated with creating a 1 mole, specifically of a pure compound, from its constituent elements in their standard states. So, and when that happens, those elements in their standard states, by definition, have an enthalpy of formation of 0. So, for example, how does oxygen show up in nature? It shows up as O2 in the gas phase. So that enthalpy for that enthalpy of formation would be 0. If I'm talking about something like silver shows up as a solid, as a single atom, and so that enthalpy would be 0. So if you just look at something and that's how it shows up in nature in that phase, then its enthalpy of formation is 0. Here are a bunch of values. You'll be looking up the enthalpies of formation for different compounds to notice. Bromine, Br2, shows up as a liquid, so its enthalpy of formation is 0. Calcium shows up as a solid. Chlorine shows up as Cl2 gas, so its enthalpy of formation is 0. So when in doubt, you could always look it up, and hopefully you'll get the hang of it, so you're not having to look it up. So how we draw it is when we write these equations for the formation of these compounds, they're our product. So we're going to be forming one of them. So starting with magnesium carbonate, solid. I want to look at all of the atoms and elements that magnesium carbonate is made out of. So it's made out of magnesium. Now magnesium shows up as a solid atomic element. Carbon shows up as a solid, specifically as graphite. And oxygen shows up as O2 gas. So that's how we write that reaction. And if I look up the enthalpy of formation, the value is, for all of these are 0. And for magnesium carbonate from that table is negative 1095.8 kilojoules. For glucose, we're going to make C6H12O6 solid. How we make glucose is from carbon. So carbon again is a solid. There's graphite. It's also made out of hydrogen. Hydrogen comes as H2 gas. And oxygen comes as O2 gas. Great. We're also going to want to balance these reactions. First, we'll look up the delta HF for glucose. We can. It doesn't matter the order, but we can look it up from the table, and it will be negative 1273.3 kilojoules per mole. So we do need to balance it. We do want to make sure that our products has a 1 value at the back. So we will make fractions for our reactants as necessary. So 1 magnesium, 1 carbon, that's good. We need 3 oxygen, so I'm going to multiply this by 3/2. And then for glucose, I have 6 carbons. I'm going to need 6 hydrogen molecules to make 12. and then I'll need 3 oxygen molecules. Okay, now we're going to make sodium chloride, solid, and lead nitrate, solid. So sodium is a solid metal in its standard state, and chloride comes as chlorine gas, Cl2 gas. I only need 1 atom though, so I'm going to multiply by half. This value is, if we look up delta H of formation for salt, is negative 411.2 kilojoules. Great. For lead nitrate, we're going to make it out of lead, which is a solid. We're going to make it out of nitrogen, gas, N2 gas, and then oxygen, O2 gas. We have 1 lead, we have 2 nitrogens, and we have 6 oxygens. So I'm going to need 3 oxygen molecules out front. We can use our enthalpies of formation to figure out what the enthalpy of a reaction could be. So what we basically want to do is take the enthalpy of formation for our products and reactants and subtract the two. So since our delta H of a reaction, change in anything is final minus initial, and since our final is our products, we'll take the sum of all of our products multiplied by their coefficients in front of the chemical reaction times by their delta H formations. So that will be for our products minus the sum of the coefficients in front of our reactants times by the delta H of formation of our reactants. So here I have, again, N is a coefficient in front of the chemical reaction, like 2 in for oxygen here. So here I have methane plus 2 oxygen, go to CO2 and 2 waters. So if I look at forming methane, forming CO2, and forming water, I have these enthalpy, reaction of formations and enthalpy of formations. Since methane is a reactant and I'm not forming it, I would want to flip it. So rather than to form it, to decompose it, that would be an endothermic, right? I'd take that and make it positive because I had to flip the reaction. And then to take carbon and oxygen to form CO2, and to take oxygen and hydrogen to form water, I'm going to release more energy. So the total reaction amount is this, negative 802.5 kilojoules. So basically what I did is I took the enthalpy of formations and I did Hess's law to them to get the reaction I wanted. So let's see that more explicitly on the next slide. So here I have the enthalpy of formation for methane, and I wrote it in the reverse direction. So I'm going to take my enthalpy and I'm going to make it positive 74.6 kilojoules. Now I am creating CO2, and so that enthalpy of formation is negative 393.5 kilojoules. And for water, to form 2 waters, that's going to be 2 times water, which is negative 483.6 kilojoules. So then when we add these all together, our hydrogens go away, our oxygens add up to 2 oxygens, our graphites go away, and we get the chemical reaction that we were seeking. So then when we add up these enthalpies down here, like with Hess's law, I get negative 802.5 kilojoules. So that was with Hess's law, using enthalpies of formation, but that is tedious. So I can now use my new formula, which is I take my enthalpies of my products minus the enthalpies of my reactants. So using the chemical formula though. So I'm going to take my enthalpy of my products, so CO2, enthalpy of CO2, plus 2 times the enthalpy of water. I'm going to subtract, so those are my reactants, or products, I mean. Oops. Products. And I'm going to subtract my reactants, so methane, enthalpy of methane, and plus 2 times the enthalpy of oxygen, which that is in its standard state, so it will be 0. So we take those values, we're going to actually end up being able to look those up in tables, which is really nice. And so I do products minus reactants, and I get the same number. So how cool that they end up being the same value, doing it in a different process. So let's practice. Here I want to find the enthalpy of reaction for this, the way this reaction is written here. So delta H reaction is going to be products minus reactants. So I have 4 times the enthalpy of NO, sum of that, plus 6 times the enthalpy of water. I'm not going to write enthalpy just because it makes it a little bit more straightforward to see what we're doing here. Minus 4 times the enthalpy of ammonia, plus 5 times the enthalpy of oxygen. So I'm going to plug in those values. Nitrogen monoxide is 91.3, so I'll do 4 times 91.3 kilojoules, plus 6 times water. Water is negative 241.8 kilojoules, minus 4 times ammonia. Now the key part here is making sure that you keep this whole thing in parentheses, plus 5 times 0, since oxygen is 0. So when we plug all of that in, and if you want, you can figure out the products, figure out the reactants, and then subtract them from each other. And if I do, I get negative 1085.6 kilojoules minus negative 183.6 kilojoules, for a total of negative 902.0 kilojoules. So I could write that, right, just like we did before. Delta H for this reaction is negative 902 kilojoules, just like we've seen at the beginning of the chapter. Let's do another one. I have thermite reaction is aluminum plus iron oxide to produce aluminum oxide plus iron. So you're going to want to use the enthalpy of formation in your textbook. This is in the back of the book, and I think it's Appendix C. So we'll do products minus reactants. So delta H of reaction is going to be products, so 1 times aluminum oxide plus 2 times iron minus 2 times aluminum plus 1 times iron oxide. So we know that anything in its standard state will be 0, so iron and aluminum will be 0. So then if we look up aluminum oxide in the book, we get negative 1675.7 kilojoules plus 0 minus iron oxide is negative 824.2 kilojoules. So I get my enthalpy of my reaction being negative 851.5 kilojoules for this reaction. Okay, here's another one. I have city of 100,000 people uses approximately 1.0 times 10 to the 11 kilojoules of energy per day. Suppose it comes from the combustion of liquid octane from gaseous water. Use enthalpies of formation to calculate delta H reaction to determine how much goes into this. So we want to first write the reaction. So I have octane, C8H18 plus O2, that's in the liquid form, plus O2 gas, goes to water. Oops, I'm actually going to do CO2 first. Doesn't really matter, but plus, and then it forms gaseous water. That's important because the enthalpy of liquid water and gaseous water will be different. So then once I balance this equation, I'm going to get, so this is a process which we've done before, so you can go back into previous chapters and look on how we balance this one. Ends up being 2, 25, 8, and 9. Great. So then after, whoops, I lied, not 8, 9. That should be 16 and 18. Cool. So So then when I find the enthalpies, so you can keep it like this. You could divide everybody by 2 to get a 1 in front of the octane. It's up to you on how you want to do that. So once you do, you get the enthalpy of that reaction to be products minus reactants. So I do 16 times CO2 plus 18 times water minus 2 times octane plus 25 times oxygen, which will be 0. So plug that in. I look in the textbook and I find that carbon dioxide is negative, so 16 times negative 393.5 kilojoules. Oops. Plus 18 times water, which is for gaseous water is negative 241.8 kilojoules, minus 2 times octane, and octane is negative 250.1 kilojoules. So when we plug it in the way we wrote this reaction, I get a value of 10,148.2 kilojoules. That's the way I wrote this reaction. So if you end up writing it with a 1 in front of octane and you divide everything by 2, then it would be half of that. It would be 5,074.1 kilojoules, and it's a negative value. My bad. Okay, so now I can write that here. Delta H equals negative 10,148.2 kilojoules. So now I can use it in my chemical reaction, or in my conversion. So if I need to produce 1 times 10 to the 11 kilojoules in a day, then I could use, and I'm producing it, so it's going to be a negative number. So I'm going to use my enthalpy of reaction, negative 10,148.2 kilojoules. And it wants to know how many kilograms of octane are necessary. So I want to go to moles of octane. And the number in my chemical reaction is a 2 in front of that. This is what keeps that a ratio. So no matter what you got for your enthalpy of reaction and how you balanced it, assuming that the balance is done correctly, but even if your factor is off, like for some reason you end up getting a 4 in front of octane and your value is 4 times as high, then it's still going to be, the ratio will be the same. Now we are going to go from moles into grams. So I'm going to use molar mass. I have 114.22 grams per mole in octane. And then I'll go to kilograms. So 1,000 grams in 1 kilogram. And the amount I need to use is 2.3 times 10 to the 6 kilograms of octane. Okay, another practice problem. So chemical hand warmers are popular with skiers and snowboarders, produce heat when they are removed from their airtight wrappers. They utilize oxidation of iron to form iron 3 oxide. According to this reaction, calculate the heat of this reaction and how much heat is produced when you use this much. So let's find delta H. So delta H reaction is products minus reactants. So I have 2 times iron oxide. That's my products minus my reactants. 4 times iron and 3 times oxygen. Now these are in their standard state, so they're both 0. This is actually the enthalpy of formation or reaction for enthalpy of formation. So I have 2 times iron oxide. If we look it up, iron oxide is, from the last problem, it was negative 824.2 kilojoules. So I multiplied that by 2, and that gives me negative 1648.4 kilojoules. So that's what I would write up here by my reaction. So if I want to use 15.0 grams of iron, then I'll use my molar mass of iron first, divide by 55.85 5 grams per mole. Now I could use stoichiometry. I have 4 moles of iron for every negative 1648.4 kilojoules produced. So that means that I have negative 110.7 kilojoules are produced or are associated with it, or you can say positive 110.7 kilojoules are produced. That word produce is implying the negative sign, that it came out. So on this next part, we're going to talk about lattice energy and within ionic compounds. So when we have an infinite kind of alternating structure where we have cations surrounded by anions that are going off in infinite direction, this is called a crystal lattice. And they are super, super stable because we have this huge electrostatic attraction that are holding them in place. And it's a lot of attraction because we have these cations and anions, and they're all next to each other, so they're maximized. And so this ends to a really stable arrangement, which means it's hard to break up. It has a lot of energy in it. That's called lattice energy. So this is the amount of energy that gets released when we break the crystal structure together. It is always exothermic, and it's actually really hard to directly measure, but we could basically use Hess's law and all of the other processes to calculate it. So lattice energy depends, since it's due to electrostatic attraction, it depends on the charges of the ions as well as how far apart they are from each other. So remember, energy equals a constant. This is kind of like an electrostatic energy is equal to a constant times, this is the important part, Q1 times Q2 divided by R. So this means if I have NaCl versus, let's do magnesium sulfide, I guess. These are both on the similar level. Now, NaCl is a +1, so the Q's, so E would be K times +1 times -1 divided by R. And magnesium energy would be K times +2 times -2 divided by R. So you could see that the energy associated for NaCl is related. If we do a +1 times -1, I have negative K over R, right? Just 1. Where for magnesium sulfide, the energy equals 2 times -2 is -4 K over R. So it's 4 times as strong, assuming that just due to the charges. Then we could also look at the radius. So if I have something like NaCl versus, KCl. Well, K is bigger than sodium, it's lower down. So because potassium has a larger radius, it's going to have a smaller energy. So we want to compare apples to apples. So we want to figure out who has higher charges, who has lower charges, and kind of group those. From there, we could arrange things based on their radius and figure out who has the bigger radius will have the smaller energy. Whoever has the smaller radius will have the bigger energy. So the Born-Haber cycle is a way that we can create sodium chloride, and basically any ionic compound from its constituent elements. So for sodium chloride, it's making salt from sodium ions or sodium atoms and chlorine, elemental chlorine. So we know all of the steps in this process other than the last one, which is the lattice energy. Okay, so you can see I have sodium plus a half a chlorine gas. So the first step here is to take our solid sodium. So sodium's in its standard state, chlorine's in its standard state. So we would first make sodium a gas, so that takes energy. Then we're going to break apart the chlorine molecules to form chlorine atom. That takes energy. Now we're going to remove an electron from sodium, so we're going to ionize it. That takes energy. Now we're going to add an electron onto chlorine. Well, that releases energy. So to go from these sodium and chloride ions in the gas state to going to sodium chloride, the actual salt that we know and love, that's going to release energy, and we don't know that. Then we can also look at going from sodium and chlorine gas to the salt using enthalpies of formation. We can calculate that. So the big thing we don't know is this right there. Now we know all these other pieces, so we could use Hess's law to find the lattice energy, and that's what they do. And you can see it's the biggest amount of energy, and it's exothermic. It gets released, and that accounts for all of these little atoms going from being apart to coming together to form this nice, yummy salt. So the trends, like we said, they are the force of the attraction, or the energy of the attraction, is inversely proportional to the distance between the ions. So bigger ions are further apart. So here we see cesium chloride versus lithium chloride further apart, and it's going to have a lower lattice energy compared to cesium chloride will have a lower one than a lithium chloride. So large ions mean weaker attraction. Weaker attraction means smaller lattice energy. When it comes to the charges, the force of attraction between the oppositely charged particles is directly proportional to the product of the charges. So the larger the charge, the stronger the attraction, which means the larger lattice energy. So here I have sodium fluoride versus calcium oxide. Again, very similar as far as where they are. Their distances are very similar, so that radius is similar. But you can see this is a +1, -1. This is a +2, -2. And they go up by almost a factor of 4 as far as the lattice energy goes. So of those two, the most important one in general is the ionic charge is generally going to be more important with regards to the strength of the lattice energy. So let's arrange these in order of increasing magnitude of lattice energy. So I have calcium oxide, so that's +2, -2. Potassium bromide, +1, -1. Calcium chloride, +1, -1. And strontium oxide, +2, -2. So we know that, based off that, we're going to have the +1, -1, potassium bromide, and potassium chloride here. Those will be similar, so we'll compare those, since they're both +1, -1. Now calcium oxide and strontium oxide will be over here with the +2, -2. So we want to look, who is bigger, bromide or chloride? We look at our periodic table, bromide is below, so it means it's further apart. So because bromide has a bigger radius, remember E is proportional to the charges divided by the radius. So since bromide has the biggest radius, it's going to have the smallest force compared to these two. So we'll have potassium bromide be the weakest, then potassium chloride. Now if I look at calcium versus strontium, strontium is below, so again, it's below calcium on the periodic table, so it has a bigger radius, so that means it will be a weaker force. So we'll have strontium oxide and then calcium oxide. So we can compare all four like this. Arrange these in order of increasing magnitude. So I have lithium bromide +1, -1, potassium iodide +1, -1, and calcium oxide +2, -2. So right away, calcium oxide is the strongest because of those charges. So we're going to put calcium oxide over here as the largest one. Now comparing lithium bromide and potassium iodide. So lithium is pretty small, bromide's really big. So small and big. Potassium is quite large, and iodide's
even larger than bromine. So knowing that, these ones are likely the furthest apart compared to the other ones. So I believe these will be the weakest because they have a really big radius. So we'll have potassium iodide and then lithium bromide. Okay, who has the higher magnitude? Sodium chloride or magnesium chloride? Now, don't let this 2 here trip you up at all. What you want to pay attention to is the +1, -1, and magnesium chloride is +2 and then -1. Don't worry about that 2 there. Just worry about the charges. Knowing that magnesium has a higher charge, oops, this should be a -1, has a higher charge than sodium, then magnesium chloride will have the highest magnitude for lattice energy because of that +2. Okay, this is the end of chapter 9. Next we will be moving into more thermochemistry and thermodynamics. But it's going to use very similar processes as what we've talked about here.